go. All right. So, quick thing before, so we started doing control of our flow. So we're going to actually, this is the fun part of programming, where we're actually starting to be in control of how our program proceeds. But before that, let's actually do a little bit more, a little bit more about the arrays that is relevant to your homework. And that is 3D arrays. So we have done 2D arrays, and 3D arrays really work in a very similar way. They're just one-dimensional, so they're harder to look at. That's essentially what it comes down to. It's harder to see, oh, did I define something wrong? Because suddenly, instead of just looking at something in a plane, which I can easily display on my screen is a 2D array of these little pixels, right? And they're very close, so I have this appearance of continuous pictures, but there's pixel next to a pixel, right? Now, if I had that in 3D, suddenly it's extremely hard to look at, and I gotta find a way to slice through. Just like when you go to the doctor and you get, has anybody done the medical CT? Good for you. That means that you've been mostly healthy. But one way to look inside a body is to actually do a three-dimensional image CT. You could do just X-ray. X-rays have been around since 1895, where you just do a projection, and then you see, for instance, bones. It reacts to the density, or it gives difference where it seizes different densities. But you can do that in 3D as well. It's just that you have to assemble that image, you have to do multiple projections in 2D, basically, and then reconstruct the three-dimensional image. And suddenly, okay, you do that. There's quite a bit of math going in, transforming those projections into the image. But then, after that, you actually have to be able to see it. So what Doctor typically gives is slices through. Okay? So you basically slice. So that's how we assemble 3D arrays. They're essentially slices of two-dimensional images put together. Now, if I were to define one, so this is just a quick interlude of how to define 3D images. And you're gonna work with one for a visualization exercise in your homework. So basically, I'm just gonna do a very basic, very simple thing. You can, I'm gonna import NumPy as NP again, just in case, so that it doesn't complain if I don't. I can define an array A, okay? And I can use any of the built-in commands that we've done before. So NP zeros will give you all zeros, right? And you can say, hey, I want, let's say that I want 3 by 3 by 3. Okay? So when you do that and you print A, you have 3 sets of two-dimensional 3 by 3 slices. Okay? And that is my 3 by 3 by 3. Now, there's multiple ways to actually slice this. If I have actually, if you think about a three-dimensional object, and I brought one little example here. So this is my three-dimensional object, right? And you're gonna get a similar one to slice through for your homework. This is actually an X-ray image that is kind of blown up. So this is really 1 millimeter on the side. And this is what's inside of a carbonate rock. Okay, it's pretty complicated, but that's basically where oil, water, and gas live and compete for this pretty limited space. Okay? Which is why petroleum engineers' work is as hard as it is. Right? So getting oil out of this ain't easy. So basically, there's multiple ways I can slice this. So when I have an image like this, you kind of have to agree. Here I have only zeros, but are those zeros going to be this slice? This slice, let's say that I have 3. Or this slice, this slice, this slice, or this slice, this slice, this slice. Okay? So those are agreements. And you guessed that different programming environments might agree on different systems. But as long as those are known and published, then you have to work with those. So sometimes there is a little bit of translating the data. Good news is as long as I get it somewhat right, whether it's I read this in or this in or this in, a little bit rotated, that's not all that big of a deal. Except that I might flip whether my billboard is this way or that way, which isn't big of a deal. So I'll let you decide whether orientations are important or not. So you have to work with it a little. So let's just work with that a little. So to get an individual element, I can just print, well, if I print any of, that's not so interesting because all of them are 0, right? But let's say that I wanted to change. I can change one element. So let's see where in these 3 slices, where is this element, the very first one, the corner, where does it sit? And I'm going to change it to, I don't know, 7. And I have to, in order to actually see that, I got to print. Aha, that's where it stores the first one. So this is where it starts. It could have really started here. Sometimes there's no way to tell of how things are oriented in the system you're working with, so you gotta play with it a little. Now, I could have done everything else, all of those colon operators that kind of replace things. I can do a range of indices, just like I can do in 2D or 1D array. So I can just replace the entire, let's see where this 0, so everybody in this slice 0, I'm trying to figure out which one of these slices that is, right? Everybody in this slice will be 7, so I'm going to be able to see where those are.
So that number 7 is to replace each element?
Each element in this, so everybody in this slice with the position 0, 0. Let's see what I get, okay? Okay. So this is my 0th position in all of the slices. Okay. Now I could have done 0, this, and I'm gonna actually repeat creating the array so that it's 0s again. Okay. So there is an entire 2-dimensional array. So I replaced everyone in this dimension 1 and in dimension 2. Those dimensions 1 and 2 are a 2-dimensional array on its own. Okay. So I have, for dimension 0 being 0, I have a 2-dimensional array. This is where it's at. Okay. For dimension 1, for dimension 0, which is my dimension 0, if I set it equal to 1, let's do this. And let's change my dimension 1 to 5. And my dimension, so this is my 0th dimension here. It can be 0, 1, and 2 because I have 3 possibilities. It's a size 3 by 3 by 3. Okay? So if I can have 3 of them, it could be 0, 1, and 2. And let's set my, so just to see where these positions sit, I came up with 3 different numbers to label them, 7, 5, and 3. I don't know, you can come up with any other. Okay?
So the first number is the number of the dimension, right? 0, 1, 2. The second is the number of the rows or the column?
So whether you want to call those rows, slices, columns, first one I would refer to slices, the way Python is organizing them. Though you can slice things in different ways. I can slice my bread this way, I can slice my bread this way or this way. Eh? They're all slices.
So it's slice.
So this slice refers to a 2-dimensional slice, right? So when I set this dimension 0, this is dimension 0, this is dimension 1, this is dimension 2. When I set my dimension 0 to a 0, all of those are a 2-dimensional array of 7s. Okay? When I set my dimension 0 as a 1, all of those are a 2-dimensional array of 5 that I'm setting to 5 just to see where they are. And then when I set my dimension 0 to 2, that's another 2-dimensional slice which is not, it's going to be set to 3 so I can see where they are. Okay? That's simply to see where does Python store these elements. And I can slice things in different ways, but I have to figure out where does Python put them, okay? So I can see, this is what I say, it's hard to visualize these things, right? Because you gotta slice it up.
Very abstract.
And in itself, it's things are, whatever is in the first slice will be in the way of me seeing through, right? So none of us is transparent. We are three-dimensional objects that are in the way if, okay? So you can see, so my 7s, it's an entire slice because that column says everyone in that dimension. So all of the possibilities that you have in dimension 1 and 2. Yes? We can actually see, I'm going to redo these zeros and then set them to different numbers. So I'm going to do the same thing just for dimension 1. Let's now say, hey, this is 0. This is everyone 1, 2. So these are also slices, okay? It's just that I'm not slicing this way anymore. I'm either slicing this way or that way. I gotta see, okay? Because I can slice this thing this way, and this way. And each slice is, I take one of these dimensions that I pick and set it to a constant. And here I'm setting this to a constant 0, constant 1, constant 2. That's picking 3 slices across this. Okay. So these are slices too. It's just the way Python prints it for me. It's kind of a little harder to see. Okay? But if I'm thinking of Python show that it has showed me these slices before, now it's showing me these slices. Yes? Before I was slicing this way, now I'm slicing this way. So there's a slice 7 that peeks through, right? It's hard to see.
It's very hard to do this
right.
exercise. Very hard.
So, but that's why you play with it until you see it. And for me, the problem is that I've learned it in a different software that does it differently. It displays you different things. And these slices, what I call when I put something like this, I call this a z direction, just I visualize it as my z direction. Well, MATLAB puts it in the 3rd spot. So now I have to flip my world by 90 degrees. So if you see me looking at something like that, that's what I'm doing. Okay? I'm trying to relate it to my own little world. But you have to play with it to just see. And then let's try the same thing as, like, there's this 3rd dimension. If I set 3rd dimension to 0, 1, 2. So this is my cube. So now I'm slicing this way. Yes? So I slice this way. Then it appeared that I have 7s, 5s, and 3s, right? And I'm slicing. Now I'm setting this slice, this slice, this slice to a constant. And just before that, I was setting this slice, this slice, this slice. Just take a knife, slice. I was slicing bread this morning, so I'm totally into it. Okay. And then, so any other routine, I could have said, hey, let's call this a B. I could have called my random rand function that gives me random numbers. And I can say 3, 3, 3, and then print B. Just like good luck seeing who is where, especially since they're randomized. It could be in any slice.
How come in this one we don't have the inner brackets?
That's just the peculiar way the rand is defined. I would expect, I agree with you, since it's a three-dimensional array, I would give it brackets.
And the fact
We
that
can try, I think it's going to give an error.
And the fact that we put 3, 3, 3 there.
It's 3 by 3 by 3.
3 by 3.
And her question is, why don't we have this, which is what we had for NP0s, and it's yelling. It doesn't like this. This is called a list of numbers. It's simply not defined to have an input. It's just whoever designed it didn't design function zeros as well. How's that? Okay? And there was nobody making sure that they have a unified look. Okay? And this is typically a characteristic of open source software. Okay? There is freedom to choose little, so every little module can have its own world. Okay? But that's also, it like leaves them be, and in time they might actually change and merge. But until that happens, but that will happen by agreement of the entire community as opposed to coming as a design from a company. Okay? When you have a company, there's a more of a top-down hierarchy, and that company is making sure that the product that comes out is unified, but that's why they're charging you for the software. Okay? Those are the differences. There's no good and bad, both are good and bad. Okay? That's just how world is. And the world should have both open software and paid for software. That's my personal view anyway.
And open source is free actually, because anyone can.
So it's free to you. It's not free. Let's not confuse this. It's not free. Okay? I am in charge of something called Digital Rocks Portal that is posting these 3D images that one of which you're gonna get for homework. Okay? It's not free. I applied for grants to the tune of $1 million to develop it. Okay? I just didn't pass that cost on to whoever is using it. Okay? I'm giving it to the, I applied for that grant, I put in the work, and I'm giving it to the research community.
Thank you.
Right? Well, but those are just different models. Okay? So that's how I decided to operate. I could have formed the company, then you still have to ask for not grants, but you have to get your funding as a company, startup company, right?
Investors.
So you have to find investors. So in this case, my investors were agencies, the little agencies that I applied to money for. But in the other case, it could be private investors. Or you could do a mix. Either way works. So those are business models, really. Okay? So in this case, Python is also developed using a lot of grants from all over the place. Some companies are actively developing it and contributing back because they came to a product that is benefiting them and they're giving back to it. As long as you have a stake to develop, as long as you figure out how to form a community to develop something, it works. That's essentially what it comes down to. Now I have laid upon you all kinds of opinions on software engineering. But anyway, yes.
Do people make programs with Python and charge people to use the programs they make with Python?
You can do that. Okay? You can also, let's say that you are your own company as a petroleum engineer, and you're going to do consulting. Okay? You build your own tools, however you want. Maybe it's from free software. Maybe it's from software that you're paying a license for. But you build your own tools. You're now in school. You're going to build a certain set of tools, hopefully, by the time you get out of it. Maybe you'll all forget about it, but maybe you want to start thinking about it. How do I think about Python or any software? It doesn't really matter which one. Any software is the extension of my thinking that will automate things for me and make them happen faster and better than you would do by hand. Right? So if you start now, as you go through the courses, thermodynamics, formation evaluation, petrophysics, you name it. If you start building your own little library of tools, you can end up with a piece of software. You can decide then what to do with that. because that is your intellectual property. Okay? So you can build on top and use it for your own consulting. You can form a one-person company and consult for other companies. You can go work in a large company and use that piece of software, either fold it into whatever you work within that company. It's you, it's how you think and you function and you build things. I'm just offering you that as a possibility of doing things, right? And all of these, that's why I'm saying that what software you use is not all that important. It's what you do with it at the end of the day. And you have to figure out what software, what help will enable you to do the work you need to do. And also understand that these tools will also change in time because things get improved. And sometimes you have to start building from scratch to improve. Okay? The same Digital Works portal that you will go to download the image from. That's the second iteration of what you're like. First thing, we just threw out a window. Okay? we got our, figured how to work on some things and figured that we didn't design things properly. And then we went to design number 2. So don't be afraid of that. And that's just the process of learning. Part of what I think is a little bit over here. Yeah?
Sorry, there.
No, it's all right.
Yeah.
Okay. Part of what's, we actually got cookies today, and that's why I was asking, are you looking for me? So anyway.
They came on Wednesday.
Well, now this is because they came on Wednesday? No, that was somebody else. So there's this, they gave little cookies that I'm gonna pass around. So everybody grab a cookie, ooh, it's Friday. So that I can actually go and talk about a little what I do for research while you enjoy some cookies. And I was like, why are they late? I need cookies too on Friday. But I'm glad we actually started this because this is what I wanted to say about homework. It's just to take 15 minutes out. I mentioned Digital Works portal. I'm going to show it to you for now. It's timely in your homework too. So rocks are images. What I do a lot is image rocks and get the geometry and figure out how fluids flow through that geometry. Okay? That simulation is quite involved. It takes a lot of computing and computing time. But part of that is I'm also maintaining a library of these images that people can visualize. So I'm going to show you some of those. And meanwhile, I just want to show you what 3D props I have. So this is a carver from Texas, from Canyon Lake. So this is pretty much called buggy. It has opening or bugs on millimeter scale. The rest of the matrix in it, it's porous. You don't see it, but there are pores in there that are on the micron size, which is basically the size of your hair. And when you zoom in those, you see something like this. Okay? So there is porosity inside what you think of as a solid rock. Any building that you pass by on campus that has limestone, there's a lot of them. You can see little shells and whatnot. Those are limestones from the area. It has porosity within, and you can actually see when it gets wet because water gets inside. Right? It dries up later, but water gets inside and displaces air that was inside before that. When we have a subsurface situation, we have oil, water, and gas. Okay? Oil and gas are hydrocarbon mixture that can, in thermodynamics, you will learn, change phases and change from gas, and sometimes certain components will separate at different temperatures and pressures. So sometimes you will have more gas, sometimes less. In either way, most of the time in the reservoir, they get those gases flow at the top, and then you have oil and then water because they stack up based on density. But in a regular situation in petroleum engineering, where you're trying to draw from the reservoir, those are gonna mix and compete in this pore space. And your job is to get the oil out and leave water behind, which is good luck. Most of the time, water wants to move. So this is kind of, think about this as a zoom in. And this is zoom in of about 1 millimeter or so. infamous shale. Okay? Pores of this are 1,000 times smaller than this. So if you want to put a drop of water on this, if you have a bottle, good luck for it waiting to come in. If you have a water bottle, feel free to splash.
So low permeability on the shale.
Very
compared to
low.
the sandstone.
So when
porosity.
pores are 1,000 times smaller, then time to get in or permeate is that to the square smaller. Okay, so millimeter. This is a fractured piece. Now this was fractured. You're going to do this in geomechanics. You're going to fracture rocks. This is so-called Brazilian test. But what you want to think about this is the following. If you're a petroleum engineer, and let's say that you want to do a water flood of your reservoir to push the oil up. Okay? If you have a fracture, this is on a small scale, they come in large, all scales, they come on all scales, from nanometer to kilometer. Okay? If you have a fracture, neighboring sort of a much tighter piece of rock that we refer to as matrix, whatever you inject here will just go through the fracture and never go to the matrix. And you're trying to displace oil that is in the matrix. So if you have, so this is my fracture going through. If you have injector here and producer here, you're going to inject and through the fracture produce on the other end what you injected. You just spent $1 million on nothing, circulating fluids in the subsurface that do nothing. Okay? You will displace stuff from that fracture, but storage in this is not in the fracture. Fracture takes 95% of the flow, but only about 5% of the storage capacity, right? And matrix the other way around. Okay. This is also why we have so many flash floods in Austin. The top soil layer is very shallow, and soil is easier to get into than a rock. There's a rock right below, so that matrix doesn't get, when it rains, it doesn't get fluids in fast enough. Then everything goes through fractures and creeks and cracks, and it goes really fast and all ends up in Colorado River, right? And meanwhile, we have these flash flooding situations because the soil, the rock is just cannot absorb everything at the rate it's going in. Okay? So that's something that is specific. Again, this is basically a piece of chalk, but that's a carbonate as well. This is what you see in your kitchens on this side.
Granite.
This is how it looks like on the other end, but it's not polished. So rocks are pretty when you polish them, but this is their real look.
And it's pretty attractive too.
And this is not something we typically produce from. Granite is typical. Granitic rock it's metamorphic rock, so it has crystals have melted and kind of fused at higher temperatures, but it's fractured a lot, and a lot of geothermal reservoirs are in granitic rocks. So in those rocks, fractures are actually really important to actually circulate fluids. Anyway, have fun with this. Can I get some here? Grab a cookie and I'm going to show you. So we have more fluids. Circulate this back. Pass it back down. So this is how Digital Rocks portal looks like. So when I actually have a water flood go through rock that is saturated with oil, then the residual oil, because in a water vet, do we know what water vet is?
No.
Yes.
Some of you do. Some of you remember from 301 and some of you don't. You've taken 301. So essentially, anytime you have two fluids on a solid surface, one of those fluids just basically ultimately comes down to the molecular forces. Okay? One of the fluid is more attracted to the rock than the other, if there are two of them. Sometimes none of them is really attracted. Okay? Then we have what's called a non or mixed bed situation. But essentially, one of them will kind of preferentially spread, and the other one will beat up. Okay. So what are the situations that you actually know really well about? So one thing that I mentioned, when you walk by, you will see that the rock surfaces are really kind of wet because water went in there readily. And if you splash some of the water on some of these sandstones, you will see that actually immediately, that it just kind of goes in. That's a wetting situation. So water wets most of the quartz surfaces, for instance. And if I have water and oil, then oil kind of beads on top and doesn't like quartz surfaces much, and water does. Now, I might have revert, and sometimes I revert it artificially. So if you know Teflon, speaking of cooking, you will always hear me do references to cooking. Teflon kind of like doesn't, you will see water, oil first bead up, but as you heat it up, it's going to also change and start wetting. So there is a temperature influence of all of this as well, okay? And that changes both viscosity and how I adhere to the surface. When you have it's raining, if you have a raincoat, okay? Raincoat is cotton with a layer of something essentially oily that repels water. Okay? So we create surfaces that are water repelling, and what happens then the water will just beat up and slide down your rain jacket. These days they will also put coating on top of car glass for the same purpose, so it's easy to wipe off that water so that you see better while driving in rain. Okay? If you go to nature, ducks are really oily. And therefore, they can swim in a very cold lake, and they're not cold because that water is not next to their skin because of the oil layer. So essentially, they have this like oils next to their like feathers and skin that repel water, and therefore they're just fine in water. Okay? So there's a lot of natural systems that adapt in that way, and we also kind of mimic them in industry. Now, petroleum engineering is an industry where you can't necessarily design your world. You can design the fluids that you push in, but you can't design the rock that is down there already. Now, as oil stays in rock for millions of years, even though I had quartz surface that was originally water wet, oil will deposit asphaltenes and whatnot, and it will basically create parts of the surface wherever oil was in contact as oil bed. Okay? So that is actually, when I have parts of the surfaces that are water wet and parts that are not, it's called mixed wet situation. So I'm going to actually show you, so this is a result of a simulation of what happens that water that preferentially wets the rock basically gets around and snaps and traps oil or gas in the middle of the pore space. I can actually show you in some of these projects how it looks like from an experiment, and there are very different projects here, but here is one where this is actually an image, X-ray image of an actual oil blob inside of a rock. Okay? So this is how it looks like when you do the surfaces, but I can say trapped oil. So this is a three-dimensional. Remember those slices that I just talked about? This is the first slice that you see. This image is 630 by 410 by 510, and will push your laptop to an extreme, probably. But I recorded a movie going through those slices. So this is a Ketten limestone. These are grains that are changing as I'm slicing. Here's oil blob showing up. This is water. This is limestone.
Where's the oil? The black?
This is oil. And this is X-ray. X-ray basically looks at the density. However, oil and water density are not all that different. Actually, not enough for X-ray to resolve. But what we do is we dope one of the fluids, typically water, with something that is at the higher end of the periodic table, like iodine. Okay? And then that iodine creates the contrast that I need to resolve where they are. You can see the contact angle between them. So you can see that this one is wetting and this one is not wetting. This is the oil that you're after in enhanced oil recovery. That black thing. But if you're not connected to it, pushing it out is called blue light. So that's what, if you are employed in petroleum industry, you have a pretty good salary because of that. Okay? So things that you can do is you can essentially try to reduce this angle. Surfactants do that. Okay? They reduce actually the interfacial tension between the two and make it easier to clean. That's what soap does too. So that's how it gets off certain things off the surface. You can design fluids that can actually push things out. Obviously, if I push more water, I won't do anything in this case. So I need to come up with smarter fluids like foams that kind of have a pretty good front. They're pretty viscous and they kind of go through and they can push a bank of oil ahead of it and kind of sweep it out, or that's the hope. Unless your foam goes into that fracture I was talking about. Okay? So then you want to try to design foams that will first plug fractures and then do the work. Okay? So that is what makes the life of a petroleum engineer more interesting. So this was let's take a look at one more project. Let's see. I mentioned sandstones. This is how sandstone looks like. This is a segmented image. This is how sandstone looks like. So you can see individual sand grains, again, as you go through, and the rest is just pore space. You can see some of the bright spots are feldspars that have a lot of iron in them, which is obviously super dense, or twice as dense as the neighboring quartz. So it kind of takes things away. Okay? And then a lot of times this image looks noisy, and it is. So there is an entire algorithm development to actually tell software, well, where is sandstone and where is the pore space. And the result of that algorithm is right here. So now you see black and white. Black where the pore space was identified and white where the... And that's typically the starting input for any kind of further analysis. I can compute porosity from here. I can just see the fraction of each of these groups. And then I can go from there and try to simulate how fluids go through. And actually this is work of my graduate student, he did. And you can actually see, it's again hard to see, and this is this 3D array business that I was trying to motivate you with today. It's hard to see, so we actually computed pressure and velocity through this, but how do you see it? Velocity is a three-dimensional object, right? So it's a vector. Velocity, at every spot, velocity is a vector. Speed is a scalar, but velocity is a vector, so it has x, y, and z component. So when you're storing it, you gotta store all three. So we have velocity, x, y, and z. And this range of values that you see is some range of numbers of the velocity in the pore space. Okay? So it's obviously kind of difficult to see where is this velocity going. So what we typically do in visualization, we try to create or visualize so-called streamlines, which are here at the beginning of the project. You kind of try to find the lines where if you put a particle or release the particle in the flow, these lines would be the trace of that particle going through. Okay. That's how you have to visualize when things are complicated. Or little vectors, but then you can do only a selection of vectors through the pore space because it's difficult to see. Pressure is easy. Pressure is a scalar, so we have only one pressure, but it's a very minimal differences. So it kind of, from the website point, it looks all white, but actually there is a range of values underneath. Okay? So this is some fun times with visualization. Any questions about this?
Where was the oil on that? Was it the white white?
This one doesn't have, this is just a single phase. So just assume you're flushing it with water, what would velocity be? Because that's how you compute permeability. So permeability you can just measure in the lab. You literally see how much water is coming up in time, and you relate that to Darcy's law and figure things out. Or you can do a simulation and average the fluxes that you see simulated, and you get that number as well.
What was your main goal in seeing the velocity?
So one of the main problems is how do I, so let's say that I have a large reservoir. Okay? I know that I have a variety of rocks in there. I drilled a well bore, I subsampled some of them. And typically these numbers, what is the permeability of each spot? I try to actually also get from just knocking on the rock and hearing back, which is what information evaluation does. However, there's a lot of models built into that. And those models have a lot of simplifying assumptions. When I'm in the simple rock like sandstone, it actually works well. Kind of everything works in a sandstone. But in more complex rocks like carbonates, it's very difficult to actually have a predictive single formula model that will just give me whatever I measure information evaluation and give me back the correct number. Okay. So because it's what's called inverse problem, I'm kind of implicitly looking at it by knocking at it. I'm not looking at it or measuring it directly. If I went and took samples and went to the lab, that's really long. That's a process that takes time. So we have to do a little bit of everything. In this world, the idea is if you get those images or get enough of them online to have a library, then I can do these predictions based on simulation and have a library that I can draw from. Because ultimately, for any kind of prediction or management of the reservoir over the long time, you have to have a good reservoir model. So that reservoir has to be populated with porosities and permeabilities at every spot. And you sampled it only at a couple of numbers. Okay? What about the million of the other points that you have in between? So there are ways of learning that, what's called deterministically, from the actual piece of rock. Then that gives me the range of values, and then I can also use geostatistics and say, well, give me random numbers between these values that are reflective of what I've measured. Okay? And I get some variability in there. So you need kind of a little bit of everything. And you will, after this class, you will have a geostatistics class that will give you the tools. How do I populate numbers that are reflective of what I measured in the lab on only a few samples? Does that make sense? Because ultimately then I create a variety of scenarios, and your job as an engineer is to kind of do what-if scenarios. Okay? What can I do to improve lifetime over 10 years? I want to exploit the reservoir 10 years, not just first 3 months. Okay, so that's essentially how it goes. Do we even have time? Well, let's get back to our class a little bit, just to continue. So any other questions before I
was wondering about CO2, carbon dioxide flooding, because I know about water flooding, and I read that they also do that, and I was like, wow.
Well,
we do a lot of
you
water
will
flooding.
get to that in reservoir engineering, but basically you have a range of tools what to flood with.
Right.
First one is water, because water is the easiest one. But then you might still need to do others. CO2 is another one. The problem with CO2, the problem and the benefit of CO2 is that it's miscible with oil, and it might lighten the oil up as it goes through. However, getting CO2 to your reservoir might be a problem. So there are certain practical problems associated with it. Third one is actually this foam, which is bubbles of CO2 in water. And just like foam that you have that you might be, look at me like I'm shaving every morning. Anyway, shaving foam is a foam. So, I'm not shaving anymore. But anyway, the foam in itself, like when you pile it up, you can see kind of it stands, right? So it has actually certain viscosity to it. Viscosity is basically resistance to flow. And foam has all of these bubbles, and their interfaces are resisting. So it's much more viscous than CO2 would be, because when you inject something that is not viscous into oil that is viscous, you're going to get something called figuring. You're not going to have a unified front, because the mobility of two phases are very different. So you're going to get one of them just kind of finding an easy channel and going through that channel, just like that fracture. and leaving the rest behind. And foam viscosifies the situation, so it enables you to kind of have a sweep front. But it's more expensive to make. So there's a lot of decisions there that you might be doing. And again, that's coming up in reservoir engineering. So, any other questions? Let's just, who needs to teach this class?
Mainly seismic, right?
Well, so seismic is a whole different set of data. Those are three-dimensional data sets too. But data in seismic is basically the velocity of my thing coming back. And then that's analyzed to give me an idea of where a fracture, large fracture, large faults. I'm looking for large faults and also larger banks. So basically, it's not like and like in any city, you will see in multiple directions. You will have the thing going around the picture with you don't know the patient.
How much happened?
That's the whole You're letting it straight up, and then it collects that. So, enough really has to pass for you to get a good response. And then you're saying, I'm wondering, what is this three-dimensional object that is away? Trying to figure out what is the object. It is something that somebody gave me. It is giving me this. And then if you have a lot of iron in one spot, it kind of sucks up all the X-ray that will give you enough response to the other. So you'll get a clean image. That's another
Find like a variable T in a later I'll use it to like redefine it, but it'll still go through the variable. Is there any way to like I don't know, like once I use it I can
right?
use it.
You can clear.
Clear it?
Yeah. And the variable. Yeah, this is because there's a class after this.
Because if you're just like,
Yeah,
like, papers as a